Okay, I guess they're all within earshot, so let me begin. Welcome, everybody. My name is Sampath Khanna, and I'm the Associate Director at the Simons Institute. Before you have fun with this workshop on managing memories, I wanted to say a few words about the Simons Institute. It was founded by the Simons Foundation in 2012, and their generous support has kept us going all these years and will keep us going for the foreseeable future. The Simons Institute is a premier venue for theoretical computer scientists to gather for sustained collaborations. But we don't have a narrow view of theory. We look for areas that a theoretical computer science perspective can help, and we organize programs that are both in core theory but also theory looking outwards. And I consider this program a little bit of the outward looking program because we are trying to see how theory can play a role in modeling and analysis and design of algorithms in these new architectures, these emerging hardware architectures. So this workshop is very much in line with all of that. I want to say one thing that's more sort of for our sake. You know that one of the best things that the Simons Institute does is the videos it puts out from all these great talks we have, and it's a great resource for community at large. And we are constantly worrying about the quality of the audio and the video and so on. We did a major AV upgrade of this room, and I think that the quality of speakers, sound and video is very good at this point. We also hoped that this would actually improve the quality of the sound for audience questions, but I've been doing a little bit of sampling, and I've found that that's not always happening. So what I would like to request is the following. If the speaker remembers when an audience member asks a question that they feel was not very loud, I would request that the speaker would repeat the question. If the speaker forgets, which can happen quite often, if someone in the audience feels that they did not hear the question from another member of the audience, they should shout out to the speaker saying, could you repeat the question? So between us, I hope that we can make sure that any question that's not very audible gets repeated loudly, and we can have for the people viewing this online, there's a more seamless view of what's happening, what discussions are happening in the room and so on. That's very important. So please, all of you have a role to play in this. Otherwise, we'll have a great workshop. I'll turn it over to Kirk, one of the organizers of this workshop as well as the program.
Okay. Without further ado, let me introduce our kickoff speaker, Rajeev Balasubramonian, who's going to give us an overview talk on the evolution of memory technologies.
Thanks, Kirk, and thanks for the invite here as well. So, as Kirk mentioned, my objective here is to give you a landscape of modern memory technologies. And so as a consequence, I'm really not going to be speaking about my own work here. It'll mostly be about work others have done, with a heavy focus on industrial trends. But I'm going to start with a little story about work that we did. The story goes all the way back to 2008, 2009, when I started working in the area of memory systems. So, prior to that, my focus had been on large cache hierarchy design. And having just submitted my 10-year package, I said, let's find some new problems to work on. And so that's when I kind of got into the topic of memory systems. So at that time, the landscape was dominated by DDR technologies, right? So that was, clearly the dominant force back then. The DDR technologies kind of were going through evolutionary changes, right? So every few years you'd see, higher capacity, higher bandwidth. But in terms of architectural ideas, there weren't, too many changes. And so if you look back at, ISCA micro conferences of the time, there were very few papers that were talking about memory systems and memory architectures. So, when we, got going on this topic, we were obviously naive and, we were trying to poke holes, and we felt, there are ways to do better, right? Just because we didn't know as much. And so the very first paper that we submitted from our group, had this title of, rethinking DRAM design. And, to this day, it's the only paper that I've submitted that got both a strong accept and a strong reject. And so, clearly would have been a very interesting, discussion of the PC meeting. I would have loved to kind of, listen in on what happened. And I'm glad, the forces prevailed where the paper actually appeared at ISCA 2010. But I want to give you a sampling of some of the feedback that we got as part of this work. It's very representative of, of industry sentiment at that time. So here is a review comment, right? So there are several major weaknesses of this paper. The paper proposes radical changes for DRAM chips, right? And so as academics, radical changes are a good thing, right? You should be looking 5-10 years out. But for the DRAM industry, that's like, no way, you should not be doing this, right? And this kind of prevailed for a good 5-6 years, right? So if you look at a lot of reviews on memory architecture papers at these conferences, they would often say, no, this is too radical. You can't make these big changes. You can't compromise on area and density, right? Those are kind of sacrosanct for the DRAM industry. So located in Salt Lake City, we were a little lucky that it's a short drive to Boise, Idaho, where Micron is headquartered. So they are clearly one of they're one of the 3 major memory vendors. And so we said, great, we're getting all these projects started. Let's make a road trip. Let's go talk to the folks at Micron. Let's get their feedback on our ideas, right? And it was a very, very depressive drive back, because we got truly beaten up on all of the ideas that we were proposing, right? So there was a lot of pushback. Some of their sentiments were essentially of the form, if you've thought about it, we've thought about it 10 years back. We've already explored it, and we've already tossed it aside, right? And so the feedback was, these circuits are so heavily optimized by people whose day job is to optimize these circuits. You shouldn't be getting into that space. Instead, accept the memory chips the way they are, and instead you should focus on systems level, application level, algorithm level innovations that can kind of exploit the features that we are going to give you, right? And I'm sure you can't read all of this, but this is a blog article I wrote after we came back from the trip. I just want to kind of highlight one line over here, which says, we were told that on commodity parts, a 0.01% area penalty might be considered, right? So there's a memory chip, and as you propose new ideas, you're increasing the area of the chip. And they were basically saying that the ideas that you put in, if it is 0.01% area overhead, that's a good thing, right? It's a very, very high bar for academics, but that's something that they would accept. 0.1% would require substantial performance gains, right? They would do it only if you give them, like a 10x improvement in performance. And anything over 0.5% was simply not happening, no matter what, right? And so that was kind of the depressing part, because every project that we were working on had area overheads of over 2%, which we thought was great, but clearly that's not what industry wanted, right? So it was a very, very depressing time back in 2010. That's why I kind of call it the curmudgeon days. Reviewers and folks in industry, all kind of beating back on this academic research. And so you fast forward, a dozen years, and now you have things from industry like HBM, right? So everybody has heard of HBM, right? It's the most commonly used memory technologies in GPUs and TPUs and things like that. And there are even things like HBM PIM. And you'll see over here that half the chip is being used for what are called TSVs, and I'll get to this later in the talk as well, right? But this is half the chip being used for interconnects, and so that's an area overhead of 100%, right? This is a far cry from the 0.1% that was the norm in 2010. And then when you go to HBM PIM, where PIM stands for processing in memory, where half of the memory is removed to make room for these compute units, right? And so at this point, only 1/4 of the chip is really being used for memory cells, and so that's a 300% overhead, right? So we've come a long way since 2010, and so that's kind of part of this talk, right? To kind of explain what has happened in these last 12 years, give some insight into what these trends are, right? And so clearly now, memory is like a happening place to be in, right? This is where a lot of innovations are happening, lots of papers at architecture conferences. And so it should be a fun target for folks in algorithms, right? Because, as this landscape evolves, there are interesting problems for all of us. Okay, so I don't know how much of that, of the tree grinder can be heard over here, but I'll plow on unless it's really bad. Yeah. All right. So what is the motivation for all of this innovation, right? So it's clearly I might want to get that window over there. Yeah. Okay. Should I try to get this one too? Okay. Yeah. Yeah, much better. right? So what has prompted all of this innovation, right? So it is the high cost of data movement, right? And again, I think this is a savvy enough crowd. You probably attended other workshops where this has probably been mentioned, right? And so, we all know that, compute is simple, it's commoditized, we can do, math operations for relatively cheap. And so a lot of the energy is going in moving data from memory all the way to those compute units, right? And so that's the stuff that really needs to be optimized. And this data movement, applies all through the memory hierarchy, right? And so, you store your data initially in registers, then there is a cache hierarchy, then you go to main memory, and then there is persistent storage, right? And, and how each of these units is designed has an impact on what folks at the algorithm level can do, right? And so even if you just look at simple registers, there are multiple ways of implementing these registers. So you can have a large register file, that's kind of what happens in GPUs and, most NVIDIA-style chips. And then you can have systolic arrays, which is what is commonly used in the Google TPUs, right? And so in a systolic array, the register file is kind of really small, right? There's a processing unit, it gets its input from one register, it produces a result, and then writes it to the next adjacent register. And so the register file is super tiny, but there's a linear number of those small register reads, right? So architecturally, these are very different. And of course, if you're implementing systolic arrays, then it's an opportunity for algorithms folks to say, well, how can I design parallel algorithms that move efficiently through these systolic arrays, have as little data movement as possible, and have as high utilization as possible, right? And so even at the register level, there are interesting connections between architecture and algorithms. And so today's talk is mainly going to talk about various implementations for the main memory, and hopefully that stimulates some ideas among you all in terms of algorithms design. Okay, so any questions at this point? I'm happy to take questions. This is a pretty long 70-minute slot, and happy to get a break answering questions if there are any. Okay, all right, so yeah.
This has been all the history of CPU main memory, on the GPU side, which is obviously becoming worse, right? Has there been a similar kind of history, or what is
Yeah. So the question is about whether there's a difference in. I've been talking about trends, and is there a difference in trends for CPU versus GPU? I would say that the GPU trends have kind of mirrored what's happening at the CPU level. In fact, I would say that GPUs and TPUs have been the motivation behind a lot of the memory innovations, right? Because I think there's a lot more investment in AI, and so suddenly kind of the bar is lowered in terms of saying, okay, yes, if I invest in this, there is going to be a payoff, right? So I would in fact say that the GPUs and TPUs have led the way towards some of the things that we're going to discuss later. Yeah. Okay, all right, so the quick overview of this talk, I'm going to start with DDR technologies, then I'll talk about stuff that is a little bit more kind of current, and then I'm going to spend half the discussion on processing in memory, right? And maybe there's a little bit of overlap with some of the other talks. I've looked at a few that are already on YouTube and tried to kind of reduce the overlap, but we can go into detail as you see fit. And then I'll end with something that's at the intersection of security, algorithms, and memory architectures, right? And again, this is just as a way to kind of stimulate discussion and stimulate ideas among you all. Okay, so let's start with the basic memory technologies, DDR technologies, right? And so, usually when I teach memory systems in my architecture classes back at Utah, the discussion on memory systems is usually the most boring and dry lecture, right? It's like, here's how rows of cells are laid out. Here's a whole bunch of, keywords and buzzwords and jargon, extremely boring. So I want to do it slightly differently. I'm going to, instead I'm going to ask you some questions and, treat it like an ask me anything, right? So, you guys ask me questions and I'll answer questions and go through it that way, right? But before I do that, I just want to kind of, remind you of what DDR technologies are, right? So this is the most common form of memory, right? So we all have DDR memory chips in our phones and our laptops and so on. Most of you have opened up your laptops and seen the memory cards, right? So this is what I'm showing you up over here, right? So this is like a DDR DIMM. If this is your board, there's a processor socket in the middle. There's a channel that comes out, and you kind of plug this in vertically into that slot. If you have a laptop, you have what is called an SO-DIMM. And so this is smaller form factor and usually kind of folds in so that it's not sticking out. right? But these are kind of the DIMMs that implement your DDR protocols. Each of the black chips that you see in here and on these, those are the actual memory chips, right? And so those memory chips are soldered onto this printed circuit board, and through these connectors, they are basically talking to your processor. Okay, and so here I'm showing you, there's DDR, DDR2, DDR3, and this is the latest DDR5 as well. Okay, so as I said, let's, I want you to ask me questions, but I'm just going to start things off by posing a few questions to you all and see if you have answers to some of these questions. So let's maybe start over here. So pick a question that you like in here. If you know the answer to one of these questions, raise your hand and I'll call on you. There's a range of difficulty levels on this question, and you're all feeling very shy. Don't. Who makes DDR memory chips? Yeah.
Why is DRAM frequency high?
I want you to give me the answer to that. You picked one of the harder questions. That is actually the hardest question on this list. So I'd be impressed if a non-systems audience actually knows the answer to why is DRAM latency high. But there's some easy ones here too. Yeah, go ahead.
So did you already answer who makes memory chips?
I did give you one, yes.
With your story about Micron?
That's right. So Micron is one of them, right? So who makes the DDR memory chips? There are 3 main manufacturers. She was paying attention. Micron is one of them. The other 2 are Samsung and SK Hynix. Yeah. So these are the 3 main memory manufacturers out there. Who wants to take on a different question here? Yeah.
I can probably try the second one.
Yep.
I think there are 2 main components. It's probably a 50-50. The first component is that you need to move data from DRAM to the processor, which is kind of 50%.
Yeah.
And another 50% is that you'll need to kind of charge a row and read data out and amplify and select the correct one and bring it to the interface of the DRAM.
Yeah, that's a great answer, right? So yes, so he's right. So why is DRAM latency high? Half of it is data movement just from the bank through various interconnects back to the processor. And then half of it is just kind of sensing the value on a cell, right? And so DRAM is basically just a bunch of capacitors. It's just rows and rows of capacitors. And the capacitor either has charge or does not. And it's a very small cell, it's got very little charge. And you're using like a single wire to sense the charge on that. It's a fairly long wire because it's spanning several cells. And so that once that cell is connected to the wire, right, there's putting a little bit of charge, and then there's a sense amplifier that's trying to detect that as early as possible, right? So half the latency just goes in sensing that little bit of charge, right? And that's why I said this is one of the harder questions, more circuits than you wanted to hear on a Monday morning, I think. But that's kind of the reason why DRAM latency is that high, right? And I kind of answered part 1 as well, right? What's a DRAM cell? It's just a little piece of capacitance. How quickly does DRAM cell charge disappear, right? Because that's why it's called volatile memory. The cell charge disappears, which means every, at periodic intervals, you have to read what's on the cell and then kind of write it back. That's the refresh process. So how often does that happen, right? So as I said a word or two, how many times did my laptop refresh memory? Or does it do it, once an hour? How often does this?
Milliseconds.
Milliseconds. So in 1 second, it has refreshed all of memory thousands of times. Seems high, right? Seemed high to me back in 2008 when I was just learning all this stuff. So how long does a charge stay on a DRAM cell? Okay, so you're not far off, right? It seems very counterintuitive. So usually the cell or the charge on a cell kind of goes away within a second for most of the cells. But because of process variation, there are some cells that are leakier than others, and you have to design for the worst case. So we are actually assuming that all cells have to be refreshed within a 64 millisecond period. So we are basically saying that to handle these worst case cells, I'm going to refresh charge every 64 milliseconds. So in a second, all of the memory on my laptop is being read and rewritten 16 times, right? So that's an insane amount of background activity happening on all of our computer systems. Right? So it's quite a mind-blowing thing to realize when you see it the first time, right? But it's not super expensive. It has a performance overhead of just about 1%, right? So there's a lot more stuff happening on our systems, right? And so recharging every cell every 64 milliseconds is not as bad as it seems at first. Okay, so I think how wide is the DDR channel, anyone? So it used to be 64 bits. The most recent one is about 80 bits. Okay, and then we'll talk a little bit more about that shortly. What is DDR? DDR stands for double data rate. So there's a clock frequency, right? There's a clock that drives the bus, and you can transfer a bit on the rising edge and on the falling edge, and that's what makes it double data rate. Okay, so hopefully that was more fun than me going through a block diagram, right? So I threw out a little bit of things you need to know about DRAM. Here's the bonus hard question. Go ahead, yeah. Yeah.
5 minutes ago you mentioned refreshing is 1% overhead. What overhead are you mentioning here? It's a time or energy or what?
So both, right? And so every 64 milliseconds you're reading stuff out and writing things back in. So while you're doing it, that bank is unavailable for other operations. So there's a performance overhead, and of course there's an energy overhead because you're kind of reading and writing back, right? And because of various techniques, it is only 1%, right? Otherwise it could have been worse. And it's projected to increase, but people have been predicting doom forever. It's not quite happened. So it's still kind of hovering in the low single digits. Okay, and so you've probably seen terms like DIM, rank, bank, array, right? And so this is kind of what makes people afraid of memory systems in general. And when you have rows and rows of bits, you can't just organize them all as like one monolithic chunk, right? And so it's usually broken up. There's a hierarchy, right? So when you have all of your all of your pictures and files, you don't put them all in one directory. Some of us do, but it's supposed to. Right? You organize them as vacation pictures and this and that, right? And that's the same thing happening over here, right? And so one group of cells is called an array, the next grouping is called a bank, and so on, right? And so you don't need to memorize these things, but I'm giving you this convenient kind of cheat sheet. So take a picture, and you can kind of revisit this anytime somebody's throwing out some memory buzzwords, right? But essentially there are all these cells, but they're kind of broken up into the smallest unit called a mat, sometimes called an array subarray. Those are organized as banks, further organized as ranks, DIMs, and so on. Okay? So, yeah.
So if you had to draw a line on this hierarchy,
yeah.
What level of parallelism is exposed to the operating system?
Yeah, so the operating system cannot see this last level down here. It can certainly see banks. So, depending on the page number, it gets placed in a specific bank. So the operating system does have control over which bank it gets placed in. If you make repeated accesses to the same bank, certainly within the page, but even neighboring pages, if you make accesses to the same to the same bank, that could impact whether you have row buffer hits and misses, right? And so that impacts performance as well.
That's all those timing attacks are doing stuff like that.
That's right? So there's the row. So there are timing attacks, and then there is row hammer, which is just trying to mess with the data. And so those are all visible to the application level and to the OS, right? And so you can craft a certain sequence of accesses that exploits, how things are placed and where the circuits are. Okay, so yeah, I think I won't go into too much more detail here unless there are questions, because this could be, this is potentially an entire lecture by itself, which may not be of, not the most exciting lecture as I was saying earlier. Okay. All right, so now let's move on. Let's talk about modern DDR and some of the properties, right? So this is kind of the picture I should have shown you earlier, right? Where there's a board, you have processor sockets, and then there are channels coming out, and then there are these kind of notches in here into which you plug your DIMMs. And so that's how modern DDR is kind of implemented, right? And so today we are at DDR5, right? And so this is kind of like the image of those DDR5 DIMMs. And then what I'm showing on the right is what you see on a GPU card. So you have the GPU down here, and then instead of using that form factor, we just have the memory chips soldered to the board and kind of directly connected to the GPUs. So it's a very different form factor. And the reason to do this is because GPUs favor bandwidth over everything else, right? The whole kind of theme for GPU design is, we don't care much about latency. We just care about kind of packing in as much compute as possible, right? Because if you get stuck waiting for something to come from memory, you just context switch and work on a different warp, right? And so the whole focus is I just want bandwidth, bandwidth, bandwidth. I don't care much about latency. And so this design kind of promotes that high bandwidth. Yeah?
It seems to me like those chips are really close to the compute, right?
Yeah.
Which would seem to make be more about favoring latency. Why does that favor bandwidth? Like, couldn't I have a high bandwidth, like longer wired connection?
I think so the question is, having these chips nearby should have also improved latency, but it does not, right? And so it is a nuanced answer, and I'll kind of get to that in a second. Okay, but I just want to kind of introduce these two at first. Now let's kind of talk first about DDR, and then I'll get to the GDDR, which is what is used for GPUs, right? So if you look at DDR5 and what has changed, so there are a few things that have been added over the previous generations, and this is a bigger change than what used to happen as we moved between these DDR generations. And so now there is support for error correction. There's support for row hammer, which is kind of the security attack that we were discussing earlier, right? And so the chips themselves have some additional functionality because they realize that the errors are so high that you can't just leave it up to the operating system and to the application level. So there is some inbuilt in-chip support for handling some errors and also handling this row hammer attack, which essentially says I'm going to keep accessing one row, and that's going to disrupt some neighboring rows. Yeah, Kirk?
You just answered the question.
Yeah, so row hammer, the row hammer attack is basically saying I'll keep accessing the same row, and if I do it about 1,000 times, the cells in the neighboring rows kind of also sometimes flip. And so there is inbuilt support saying I can detect that you are kind of hammering one row, and so what I'm going to do is I'm just going to refresh that row and the neighboring rows, and then that just basically kind of restores charge and essentially resets that attack, right? And there are papers written on this because the first industry attempts were not very good, and so people have kind of also defeated those inbuilt defense mechanisms as well. Okay, the other big change is thermal and power management is a much bigger deal, and so some of that control is moving onto the memory itself, right? It used to be entirely handled by the memory controller, but now there is some support on the DIMMs as well. And then the never-ending improvements in signaling and signal integrity has also helped, and so they're supporting higher bandwidth, higher capacity, right? And as I was saying earlier, used to always be a 64-bit data channel, and now it's kind of been broken up into two 40-bit channels, so 32 bits of data, 8 bits of metadata for error correction. All right, and I'm just kind of, all through this talk, I will end my slide with a few numbers, which, to me are a little boring. They're going to keep changing. But again, this is hopefully a handy cheat sheet for some of you, right? So if you want to look up, how fast is modern memory, you can see some of the capacities and the clock speeds over here. Okay, so with that, let's now go on to GDDR7, right? And I'm going to answer his question on, why is it higher latency, right? So the distance is only one piece. What really matters is what frequency can you drive the bus at, right? And so when you have a shorter wire, you can actually drive it at a higher frequency, right? So moving the chip right next to the processor allows you to increase the clock speed and hence improves bandwidth. And so that's a huge piece of it, right? You can see that over here there are all these copper connections, and so you're kind of plugging it in, right? You can see it's a very clunky connection, so obviously you can't drive at very high speeds, right? Your signal integrity is not going to be as good. When you can actually solder the pins to each other on one printed circuit board, you're going to get much better signal integrity, right? So that's one huge piece of it. The other trick that people use to get high speed or high frequency is to use something called serialization deserialization. So instead of having a parallel bus, you implement a narrow bus where the wires are sufficiently apart for good signal integrity. And when you're given 8 bits of data, you actually re-encode it to become like a 10-bit entity. And that allows you to send a 10-bit entity in a serial fashion, which has better signal integrity even at high clock speeds. So that's how you get even higher clock speeds. Instead of actually just sending a 0 or 1, you kind of re-encode the data so it's in a better format. And that allows you to kind of change the frequency even faster. So that's how you increase the signaling frequency, right? So over here, you have 48 gigabits per second, which is an order of magnitude higher than what you saw on the DDR slide just previously. Okay, now what that does is before I can send the data, I have to encode the data. So there's some encoding and decoding that happens. That adds to the latency, right? And so that's why this, so this seems like a great trick, right? If I can get higher frequency and higher bandwidth this way, let's do it on the CPU as well. And it's not done on the CPU for multiple reasons. One is because of these clunky connections, you can't get that higher frequency. And secondly, it adds to latency because now I have to encode and decode the data, right? And so in GPUs, right, because you don't care as much about latency, you're able to kind of pull off this trick where you get higher bandwidth, but and higher latency. But I don't care about latency here. So that's how the GDDR7 generations are a few steps ahead in terms of bandwidth. Okay, so that was a nuance and kind of like a circuit-heavy answer, but that's kind of the distance is only a piece of it, right? What really matters is frequency. And latency is affected more by these other things like what is called SerDes, serialization, deserialization, latency. Okay, questions? Right, so don't be alarmed if I get into some of these rabbit holes, right? You don't need to understand every single thing I say in these in the 70-minute talk, right? But hopefully there'll be bits and pieces for everybody. Yeah, go ahead.
Serialize, deserialize happen between the core and every memory.
Yeah, so there's an interconnect. And at the two ends of the interconnect are the transmitters and receivers. That's where the encoding, decoding, or the serializing, deserializing happens.
And this is not adapted in the CPU space?
So PCIe, right, which is how we do I/O, also uses serialization, deserialization, right? So there you're basically saying that, oh, I'm doing I/O, that's going to be plenty slow anyway. Let me optimize my pins and implement them at high bandwidth using serialization, deserialization. So it does happen in the CPU as well, but it's not done for the memory system, it's done for I/O. And you will see that kind of re-emerge a little later in the talk when we talk about CXL. Yeah?
Should I think about the encoding as like a error correcting encoding, or what
yes, yeah, it is very much like that, but with a different objective function, right? Here you're not trying to reconstruct lost bits. Here you're trying to do encoding that improves the signal integrity.
Oh,
so there's a sufficient difference between two bits being transmitted that I can flip the clock fairly quickly and I can still kind of extract what was being sent. Okay. And you have kind of maxed out my knowledge on this topic, so don't ask me any more follow-up questions on that. All right. That was a question for Mark Horowitz when he was here a few weeks back. Yeah. Okay, all right, so I think I have covered all of the nuanced points I mentioned. Well, there are other things, right? They're even doing higher voltage, that usually improves speed, right? And that also increases power. But that's why GPUs and these graphics cards have very different objective functions, right? They don't care as much about cost. They already know you're kind of paying through the nose for these things, right? They already know that it's extremely high power, right? And so they just basically say, yeah, I just want to maximize bandwidth, and I can make all of these other trade-offs that give me that high bandwidth. Okay. All right, so that was DDR technology, right? And so kind of what are the take-homes, right? So we went into a bunch of rabbit holes. What's the main takeaway from this? Well, thankfully, technology scaling is continuing to help us, both in terms of the chip capacities and in terms of signaling innovations. But the other big change that's happening is we are putting more and more functionality into memory, right? It used to be just these dumb rows and rows of bits, but now they're doing a few other things as well, right? They're doing error correction, they're doing kind of the security defenses. Like we talked about earlier, they're handling refresh, and you'll soon see that they're also going to be handling compute, right? They're actually going to be doing some number crunching in addition to just kind of storing all of these bits. Okay, so now let's kind of fast forward a few more years, and let's talk about the next kind of big innovation that has happened, right? So most of the high-end GPUs and the TPUs that are used in Google data centers, they all use what is called high bandwidth memory, right? So they're all using this new technology, where what try to look at all of these three figures at the same time to get a feel for what it looks like, right? But essentially, you have the processor and you have your memory, right? And usually, you have like a printed circuit board like this, and you're kind of making the connections with wires that you can actually see, right? So this is not like a nanoscale wire. It's it's maybe a millimeter scale wire that you can actually see. And that bandwidth was not enough, right? We wanted to increase the bandwidth even more. So what is done is you get what is called an interposer. It's a silicon block, and you're kind of putting your GPU or your TPU on that, and then you're putting your memory next to it. And you're using the metal layers on the silicon to implement the wires, right? And so you're not etching on a printed circuit board. You're using, photonics and things like that. I shouldn't have said the word photonics here. It's not a photonic connection, right? But all of lithography, all of the manufacturing process uses these very precise lasers to kind of etch things at nanometer scale, right? So that's kind of the photonics I'm talking about, right? And so you're using CMOS technology to implement these extremely fine wires. And so that's what gives you very high bandwidth, right? And so that's referred to as 2.5D stacking, right? Because yes, it's a 3D structure, right, where you're putting one processing chip and one memory chip on a piece of silicon, and then using kind of metal layers over here to give you that high bandwidth connection. To increase capacity, this is not just one memory chip, it's a 3D stack of memory chips. Okay, so just to kind of give you a feel for the scale, right, I'm going to use one of my show and tells over here, right? And so this gray Lego piece is your interposer, right? And on that is the processor. Next to it is the memory. I really should have made a 3D stack of memory. I remembered it and then I forgot to go back to the basement. But there's a 3D stack of memory here, there's a processor here, and they're connected with these wires. These are very thin wires because they're using CMOS technology. Usually to connect the processor and the memory, you use wires that look like this, right? So that's kind of the big change over here. Usually the wires look like this, but by using an interposer and by using basically CMOS technologies, I'm actually implementing these wires at very small dimensions that gives me that high bandwidth. Okay, and that was my last show and tell for the day, but right, but hopefully that gives you a sense of the scale, right? So that's why I'm getting that higher bandwidth. What that also means now is from this chip up here, this memory chip up here, I have to drill a hole that goes all the way down here. That's called a through silicon via, and you'll see that half the chip is being used for that. Right, so the days of mocking people for adding area overhead is now gone. Now you have license to drill holes and use half this chip area to get that high bandwidth. Okay. All right, let me just see if there are a lot more details here. I don't know if I go through every single one, we'll take a large amount of time. So I don't know if I should. Let me just pick on a few highlights, right? And so, on one chip you have several banks. The banks are all multiplexing into one channel, which then kind of goes down on the 3D stack. But every chip has its own channel. So the more memory stacks that I add, right, the capacity and the bandwidth increases. It increases linearly. Okay, there's also usually a base logic die that's used for buffering and test, but you can imagine doing other things on that as well, like maybe processing. Okay, and so there are some more options over here, and then like with every slide, I have the latest numbers here. It's not uncommon to have 6 HBM stacks next to one of your GPUs and TPUs. And so that's a whopping bandwidth of 7.2 terabytes per second. Right? Also gives you higher capacity, 384 gigabytes. Right? If I go back a couple of slides, if you look at a GPU card, the GPU, in fact, let's go to this image over here. Right? How many memory chips do you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each one has a capacity of 16 gigabits. So that's a total capacity of only 24 gigabytes. Right? So a GPU card has limited memory. Right? You get a lot more on a CPU. Right? If I go to my DIMM, right, it's got the DIMM capacity is 256 gigabytes, because this one chip has can have like 32 of these black chips on it. Right? And so that's why, again, different trade-offs between a GPU card and CPU memory, and look at how much more capacity you get. Right? That's why this is high-end. Right? Those memory chips are very expensive, and you're paying that high price to get this capacity and this bandwidth. Yeah.
Does removing heat limit how much stacking you can have?
Yeah. So heat is a big concern. And so when you have 3D stacking, right, there's all this power being generated. Memory chips are better than number crunching units, right? Because there's all the space, but there's a very small piece of active silicon. Because when you're getting data out, there's only a very small fraction that you're actually activating. So memory chips are nice in that way, but yes, they also have a heat problem. So there was like a projection from an academic place that talked about, what's the next few HBMs going to look like, and there's like one column for, how are you going to cool these things, and it gets, more and more exotic as you go from one generation to the next. So that adds to the cost, but again, remember this is the segment where people are willing to pay through their nose. Yeah.
Frequency scaling, one thing being considered for that?
It is certainly a huge consideration. I'm glad you are bringing up points that I forgot to mention earlier.
What was the question?
Yeah, sorry. Yeah, so thanks for reminding me. Right. So the question is, can you use things like dynamic frequency scaling to handle the power issues? So in DDR5, right, there is this power management integrated circuit. It's got these temperature sensors. So DDR5 is absolutely doing that. Right? It's realizing things are getting too hot, and it's modifying the frequency to control the power dissipation and the thermal emergencies. I don't know if HBM is doing that. You would think it's got the same stuff included, but I didn't run into that. I haven't run into that yet in my readings. But I won't be surprised if that's part of it, right? Like people are doing it in other segments of the market. Okay. Yeah, go for it.
Sorry, another question. You've mentioned that through silicon VS is taking 50% of the space. Is that a limiting factor for us to stack more HBM that will cause?
Yeah, so there are multiple challenges. So the question is it the through silicon vias that are a limiting factor in terms of stacking? So multiple things, right? So when you make these through silicon vias, each layer adds to its complexity, right? It's like if you want if you want a chip with high yield, fewer layers is much better, right? But again, you can compromise on yield if you just want that high bandwidth. But that is certainly one of the limiting factors. Heat is the other limiting factor. So I think there are several problems that have to be overcome if you want to go from 16 deep to 20 deep or 24 deep. Yes, all of these play a role. Okay, and so this is that kind of, I talked about using up half the area, right? So this is kind of one good code that gives you the bottom line numbers. So in traditional DDR4, you have a density of almost 0.3 gigabits per millimeter square. In HBM, that's all, that's nearly 2x lower, right? So this is kind of highlighting the fact that, I know I've given up, or there's 100% area overhead in order to get that higher bandwidth. All right, so now shifting gears a little bit, right? So we're, again, still in the theme of what's kind of state of the art today. Let's talk a little bit about non-volatile memory, right? And so why did people start even looking at non-volatile memory? Part of it is because of the limits of DRAM cell scaling, right? So I talked about one cell being one capacitor, and I think in tomorrow's talk, Moin Qureshi will definitely have a figure that shows you like a deep capacitor, right? And he'll talk about how that does not have structural integrity, right? It's like building like a very tall tower of Lego bricks. Again, I could have brought that show and tell. Maybe Moin will do that tomorrow, right? But if you build like one really tall tower, it's not as stable. And so people are saying, we need to find some other alternatives. What else can we do, right? And so they found the non-volatile memory cell, which I'll show you on the next slide. And maybe this is a good time to show you how that's done. So you have silicon, and then you have metal layers on top of the silicon. And so when you have metal layers, on the first layer, all the wires are going in this direction. So all the blue stuff that you see. On the next metal layer, you have all the wires kind of going along the x dimension. And every time they overlap, right, there's like a small overlapping region. And what you're doing is putting some resistive material in that overlapping space. Okay, so what you end up getting is like a crossbar, right? It's basically, intersecting x and y wires and cells at every intersection point. And so the cell is, very, very dense. And in fact, you can have more metal layers, right? That increases the cost, but not as much as some other strategies to kind of add density, right? And so you can have more stacks of these metal layers, and so you get like a 3D kind of pattern of these cells. So this is what non-volatile memory kind of looks like, and that's why the Intel Micron product that many of you probably heard about is called Crosspoint, because it's kind of the name comes from this kind of crossbar structure. Okay, and so this is great in terms of density. Because you're using resistive material, it is naturally non-volatile. That means even if you unplug it, the resistance of the material is still going to stay the same, right? So the high resistance or the low resistance, which represents 1 or 0, is going to persist even when the system is unplugged, right? So the non-volatility is almost like a bonus. It kind of, we were not really trying to do that. We were just looking for high density, but we got non-volatility as well. Okay, so the read latency is not super high, right? Or it's not much more than DRAM sensing latency. Writes are more problematic, right? They take more time, they consume more energy, you have to do it multiple times till you get it just right. And all of that kind of breaks down the material as well. So these devices have limited endurance. They can handle like a certain number of writes, and after that they kind of break down. Okay? The other big change with this is it impacts the software. So if you want to take advantage of this, you have to kind of find ways to use it either as a file system or as persistent memory, so that even if there's a crash, you can recover your data that is usually lost when it's sitting in memory. Okay, but you have to be kind of mindful of writes that might have been in transit, right? So some bits got written, some bits did not get written. How do you recover from that kind of weird transient state? Okay, so this is the famous product I mentioned earlier. So Intel had this Optane technology that was in the market for a few years, has now been kind of discontinued for the most part, and partly because the technology was not mature enough, right? There were other things that were improving at a faster rate, and so it was not profitable given all those other competing products. There were two different ways to use it. I won't spend a whole lot of time on this. There's one really good paper that I'll recommend for future reading if you're interested. So this is almost like a 50-page paper from Steve Swanson's group at UCSD, and it very thoroughly characterizes that actual commercial product. Okay, any questions? I'm going to do one more topic before I get into processing and memory, and that is memory interconnects, right? So we're talking about go.
So is there another? Are we going to see another NVM in the near future? Or?
Yeah, it's unclear. I haven't heard any inside information on whether there is something new upcoming. My expectation is, you absolutely would, right? The clear trend in the memory industry is to put more functionality and more features, because if you want to sell more things, you have to find some way to add value. And so things that were, not considered on the table before, should absolutely be on the table moving forward, right? And so, there's a lot of research still being done on non-volatile stuff. And so I expect that, there will be some breakthroughs in the coming years. Yeah. But yeah, that discontinuation absolutely, took some of the air out of the balloon. Yeah. Right. So again, I know I'm going through a bunch of stuff. So let me just take a second here to remind you of where we are in the stock. Right. So I first talked about DDR technologies and the latest stuff that has happened there. Then I talked about the high bandwidth memory. Right. That was the next big innovation that happened. I'm just going to talk about a couple more before I talk about what I think is the most exciting thing for the future, which is processing and memory. Right? And so we talked about non-volatility. I'm just going to talk about CXL, which is a way to kind of modify the interconnect so you have access to more memory. Right? And so there have been lots of attempts in the past of trying to scale up the memory capacity. And industry seems to have kind of converged on CXL, which is a better version of a PCIe interconnect. And what it mainly does is it allows you or gives you a way of accessing a larger address space, which can be cached and which can be kept coherent as well. Right? And again, since I'm not spending a lot of time here, the best reference that I would recommend you read for this topic is this introduction to the CXL interconnect, which is again like a 40-page paper in the ACM computing surveys. Okay, so it's good to find good literature here. I think this is the best and most detailed one that I found. Okay, but just as a 1-minute overview, right? So what you have is your host processor, like an Intel chip, with its own last level cache. That's what LLC is. CXL controller, which used to be a PCIe controller, and then you have other devices that you can kind of plug in, right? And so here's an accelerator with its own cache. and its own memory, and potentially, and well, of course, you have your own memory on the host as well, right? And so in the past, if there's memory over here, there was no way for the host to cache that memory, right? Because this memory was not part of this host's address space. And so, this memory could only be used in kind of like a streaming I/O mode. And so that is now being modified with CXL, where this stuff is part of the address space. And so it is the CXL controller's job to kind of route requests over here. When it comes in here, it can be cached. And now when there's an update over here, the updates get pushed into this cache as well, right? And kind of vice versa as well. So this one can also cache this one's memory. And when there's a change being done here, it gets pushed down here as well, right? Again, that is something that was not available in the past. So that's the coherence aspect of CXL. And so the protocol is broken into 3 different parts. I/O, which is kind of the conventional PCIe protocol. The memory stuff, which expands the address space. And the dot cache, which makes sure that updates are pushed to these other devices. Okay, so that's only scratching the surface of CXL. And as I said, if you want to learn more, I think that reference is a great place to look. All right, so that's part 1 done. This is usually, in my lectures in the classroom, I usually take a 5-minute break at this point, but let's not do that. But yeah, question.
So the CXL is an interconnect technology, right? Similar to PCIe.
Correct.
So how does the NVLink, UA-Link compare to this? Is it something similar?
Yeah, so those are all proprietary protocols. Like the NVLink is only for like NVIDIA products. So CXL is kind of trying to take the best of those ideas and do something that's like an industry standard. But yeah, there's going to be a fair bit of commonality among all of those interconnects. Yeah. Okay, so the main take-homes, right? So from all that we have seen in kind of what I'll call conventional memory, what we are seeing here is that high latencies continue to be a problem, right? We are not really working very hard to solve the latency problem because as he articulated earlier, those are fundamental problems, right? You cannot reduce latency a whole bunch. You can do a lot better with bandwidth, right? So we've improved bandwidth a fair bit, but there's still more needed, right? We still need to improve our bandwidths, and that's where processing in memory kind of comes in. We're also seeing these hierarchies getting deeper, right? Sometimes there's NVM, there's sometimes CXL in the way. All of that means that you'll see different latencies to different parts of memory, right? And so there's still a fair bit of cost in data movement, right? And so we've seen some improvements, but lots of problems continue to remain, right? And so we're going to try and address some of this data movement bottleneck with processing in memory. And this has been a topic for 30 plus years, even beyond that. And there's been significant headway in the last few years. And so I'm going to give you a few examples of processing in memory, and some of these are commercial examples. And so that's been a huge shift in the last few years, right? And I think there's some very interesting programming models over here, which is why I'm going to try and do an overview of these different architectures. Okay, so you'll also see this terminology: processing in memory, near memory, and using memory. When you're using memory, you're basically saying that the stuff still stays in memory, and I'm going to use some circuits to do some arithmetic on the data. Okay, and so very often they're kind of analog arithmetic. Processing near memory is when you use like an adjacent logic die to kind of do the computation, and then processing in memory is when you again have like a compute unit, but it's embedded inside the DRAM, right? If that doesn't make a lot of sense, we'll soon go through some examples. Okay, so here's the first example of processing using memory, and so here's that crossbar structure that I showed you before, right? So wires that go in the X dimension and the Y dimension, and at every kind of crossover point, there's some resistive material. So when you apply voltage V1 over here, depending on the resistance over here, there's some current that gets injected into this vertical wire, right? It's V1 divided by R1, right? That's the classic Kirchhoff's law. Expressed over here is V1 times conductance 1. If there's a second line on the same bit line, that also injects some current over here. So the current that comes out is V1 G1 plus V2 G2, right? And so this circuit, just using natural Kirchhoff's law, can be used to implement dot products, right? Very, very useful for AI workloads. And so there was an architecture that came from our group, right? Which was basically implementing a large neural network across a tiled architecture. And so you kind of have a pipeline, you have a spatial pipeline. You'll see that the weights are kind of embedded inside this crossbar. And so maybe the weights for layer 1 are embedded here, the weights for layer 2 are embedded over here. And so the activations basically go from layer 1 to layer 2, but the weights never move. So you're never expending energy to kind of read the weights out. Right? So this is an example of processing using memory, where the data movement is only for the activations and not for the weights. Okay? Any questions about this? I kind of, this is like a whirlwind summary of that work. Yeah?
So this seems, I learned about this for the first time at the boot camp.
Okay, yeah.
But this seems, it's great for the current AI, because it's exactly, it does dot products, right? It's not, it doesn't do general purpose computing like some of those.
Correct, yeah.
What happens if we realize in 2 years that the way to do AI is not dot products, but something else? Do you have to completely redesign this, or do you think this is more general?
So the question is, this is highly application specific, and so what happens if the algorithm were to change, right? And so you're absolutely right that the more specialized the architecture, the less applicable it might be for the workloads of tomorrow. The objective over here is to provide like a basic primitive, which is the dot product. And the hope is that that is not going to change, right? So maybe you change the activation functions, maybe you do some other normalization in between. Those will need some programmable units, right? So there are some other kind of supporting circuits which are programmable. And so you try to make sure that this is as programmable as possible. But you're right that if the dot product changes, then this is not worth much. And so that's always the risk that you take as you kind of go for this customization, and that's kind of the that's the source of energy improvement, right? The less general purpose it is, the more throughput and the more energy savings you're going to get. But there's always a risk involved in going down that route. Yeah. Okay. Yeah.
So in this example, so the G is fixed, right?
No, it can be changed. So that register over there is programmable, and it can have multiple different values. And so you can go in and kind of modify each one to represent the weight that you want. But once you program it, it hopefully stays there for a large amount of time, because with all these devices, wear out is a concern. So you can't be changing it all the time. And if you're changing it all the time, you're kind of defeating the purpose of the in-memory computing. So you're hoping that you just put the weights in and just stays there, right? And so this part of the circuit is always doing layer 1. It has the same weights. You don't have to switch weights out when you go to layer 2, right? That happens on a different tile. So that's why we call it a spatial pipeline, right? Whereas in a GPU, the weights are are constantly context switching, and you're using the same compute resources for layer 1 and then again for layer 2. So it's a very different architecture. Yeah.
Does this allow you to do things in pick your precision?
Yes, right. And so I was telling him that the resistances could be anything. I was kind of exaggerating a little over there, right? So based on the technology, maybe you can only put in 2 bits worth of content over here, right? So maybe you can only distinguish between 4 different resistances. So you have 2 bits over here. If you want to work on an 8-bit operand, you use 4 of these in parallel. And so with that flexibility, yeah, you can do even 16-bit if you wanted, right? And so what you're providing here is a basic primitive that does like 2-bit arithmetic over here, and then you kind of put together, there's more layers of abstraction to get higher precision. Okay, all right. So now let's talk about a couple other industry approaches to getting processing in memory, right? So UpMem was a startup in France, recently acquired by Qualcomm. Here's their first generation chip. So this is something that you can actually buy and experiment with. And so let's spend some time on what this architecture and what this programming model kind of looks like. Just keep an eye on the time too. Okay, so here's the host CPU. You have regular memory connected to it, and then you have UpMem DIMMs connected to it. And each UpMem DIMM has a bunch of memory chips, right? And let's kind of zoom into one bank. So you have one bank of memory, and next to it is an in-order processor. It's an 11-stage processor, fairly simple processor. What you have to remember over here is that when you're implementing things on a memory chip, these are designed for low cost. It's only got 3 or 4 metal layers. And so your interconnects are not going to be as high quality. Even your logic is not going to be as high quality. So an in-order processor that runs very fast in a class project on a logic process does very poorly over here. And so in fact, when you have two dependent instructions here, there's an 11-cycle gap between those two dependent instructions, right? And so that would just cripple your utilization and throughput. And so they alleviate that effect by saying, let's just do multi-threading. So you can have 24 threads running in parallel. So two back-to-back instructions are actually from different threads. The dependent instructions of one thread are actually separated by a whole bunch of cycles. And so you're kind of keeping things as busy as possible, right? So it's almost like a GPU-style design. The one big difference from a GPU is that this is not single instruction, multiple data. Just doing one computation every single cycle, right? So there's no way for this to compete against GPUs, right? GPUs are going to give you much higher throughput, even though this gives you much higher memory bandwidth. Okay, and so that's kind of, again, this is a first generation product. Even though I'm criticizing it, got to acknowledge that this is the first stake in the ground, right? So pretty impressive to kind of have the first commercial design that does this, right? But the one major drawback here is, there's no SIMD. Okay, I'll talk a little bit more about this programming model in a second. Let me just talk about another commercial effort, right? And this was published at ISCA 2021. And this is the figure that you saw earlier with the HBM. And what they're saying is, let's take that HBM, take away half the memory, and instead put in some compute units. And so you have a 16-wide vector unit, right? So this one is now SIMD, so it's got much higher throughput, right? But kind of using the same principles and saying that, let's do some execution right next to the banks, has access to a lot more memory bandwidth and has a lot more execution bandwidth because of the SIMD nature. Right? Let me just talk about a few other highlights over here. So I already talked about the 16-lane SIMD. You can have your inputs either coming from the memory itself or from registers. Okay, and so the programming model kind of looks a little bit like this, right? So at first, you are in the normal memory mode, which is kind of the single bank mode. And then what you do is you say, well, I want parallelism across all my banks. I want some compute to be done. So I go into this all bank mode. I first send like a program into each of these banks saying this is kind of the sequence of operations I want to get executed, right? But there are no operands just yet. The processor then issues additional requests that say, I want to deal with this particular row. And when that message shows up, there's a certain row that gets read out. And then you look at this command register file to say, what operation did you want to get done on that? And so there is a program that you've kind of preloaded, and then the processor continues to kind of, control it at a very fine grain. It keeps sending addresses saying, I want you to do this operation on this particular row, right? And so it's kind of like it's a very interesting programming model where the host is, doing some offload, but then kind of still staying very involved. Yeah.
So I'm wondering if this was for the following applications. So
yeah.
Sparse linear algebra and many other applications, you want to do indirect addressing. You read in a row of indices, and then you want to go back to memory and fetch those locations, maybe increment.
Yeah.
And right now you have to go all the way back to the CPU and say, please load this again.
Yeah,
that's if that could be.
And I don't think it helps with that. I do not think that it can support that kind of application, right? So in the papers that kind of describe this architecture, they mostly focus on the classic machine learning workloads, right? They don't talk about indirection. I don't think that is easy to do because in this design, the addresses are being generated by the host. The host says, here's the row I want you to work on. You know what operations to do, but here's the address. In what you're proposing, I think you're trying to do some indirection saying, I just read something. That should generate the next address without it being sent all the way back to the host. And I don't think that's allowed, right? I don't want to dismiss it just yet because there are some registers here which maybe allow you to do something, but I think it is difficult because the address has to come from the host. I don't see how you can somehow shoehorn address generation into the chip itself. But again, these are all first attempts, and I think they are targeted at a few lucrative markets, right? And I think the problem is up to us to kind of figure out, well, what can I do to kind of massage this into a form that applies to more workloads, right? So very much an open problem, right? This is what you're seeing here is first generation implementations of processing in memory. Okay, but I hope the programming model is a little clear. It's, it is a little bit complicated, which also means that these are some interesting challenges for all of us. Okay, yeah.
I brought up source algebra because machine learning is increasingly using.
That's true. Yeah. That's true. Yeah. So I didn't want to dismiss it as a not non-lucrative segment. Yeah. But they've taken some of the easier stuff first. Yeah. Okay, I'm going to skip this one in the interest of time, but yeah, go ahead with your question.
So what is this actually used? What is the commercial uptake?
Yeah, so Samsung definitely has a prototype, and they have a software ecosystem all designed there. They have silicon that's up and running. It's not something you can buy today. So, and I don't know what the
paper was like 2021, right?
That's right, yeah.
5 years and nothing.
In 5 years, there is no commercial product that you can buy yet. Yes. So it's not clear what the roadmap is. Like I'm not plugged in enough to know what the current status is. Okay, I'm going to skip this. Let's just kind of talk about this overview over here, right? So LLMs, of course, are very GemV heavy. GemVs, do very little compute for every byte that you fetch, and so they're a perfect fit for PIM, right? And so there are many different flavors of PIM. We talked about in, near, and using, and then there are additional ways of implementing those. So lots of opportunities, programming models, architectures, compilers, schedulers. Okay, so in terms of time, right, I should start wrapping up. I do want to talk about, so I think I'll probably skip the case study that I promised you. It's a case study on oblivious RAM, which is like a security primitive, right? And so if you're interested in ORAM, I can talk to you for hours about it, but it is an esoteric topic. So maybe that's the thing I should probably skip. And let me just end with a few slides that just kind of talk about the take-homes in terms of memory management, right? And so we've just talked about processing in memory, which I think is going to be an exciting technology. If you have that platform available to you as an algorithms person, what can you do? And what programming model would you like, right? Like we were just discussing. In fact, that last question, right? It kind of highlights the limitations of existing hardware. Right? And so it's up to you all to figure out, well, this is how I'm limited. If you gave me these additional features, this is how much more I could do. And it is that push that then tells companies like Samsung and Micron to invest in adding these features. And I think the bar is now a little easier to scale, right? Once you've already dedicated like a 300% area overhead to do this, there's nothing wrong in taking that up to 310%. Right, and so I think this is like a fertile time to figure out what's a good programming model and what can you add. Okay, so now let's just take a look at UpMem. So in UpMem, there's only one device that can access memory at a time. Right, so you're basically saying that I'm going to copy my operands from regular memory into UpMem memory. I'm going to offload my program, and then you can go off and run. Right, and while the PIM code is running, the host processor cannot access that memory. So there is no concurrency, and that's like a fundamental problem in DRAM. Further, the PIM unit can only access its local bank. It can't go and access the data sitting in other PIM banks. Right? So these are all kind of fundamental constraints and limitations. Right? And so a key problem over here is how do you marshal data? How do you enable versatile access? Right? And so if your data is not sitting locally, can I still access something that is a little further away? While the PIM units are working, what can the host processor do? Right? There's all that compute sitting there that is potentially idle. Right? How do I take an application and parallelize it so it can use the host and can use the PIM units while abiding by all of these constraints? And like he was asking, what more can you add so that things like indirection, what are the additional features that you would like? Right? So lots of open questions over here. I just mentioned one quick hack that UpMem did. Right? So this is the DRAM bank. Only the host or the PIM can access it at a time, but not both. Right? And that's because there's all the state over here, and that you can only have one memory controller that's handling that state. And so the hack that UpMem introduced is they said, well, there's like an SRAM scratch pad, like an L1 cache, and it's much easier to implement concurrency over here or concurrent accesses over here. And so they have a hack where the host can actually, while the PIM core is running, the host can kind of sneak in and modify some data over here, right? And so you can implement a task queue, right, where while the PIM code is running, there's a task queue, and the host can say, well, here's a new task I'd like you to take care of. And similarly, you can get your responses back through this as well, right? And so these are kind of hacks that they introduced but it's worthwhile to think about, what's a good programming model, what's a nice abstraction that makes this concurrent access possible. Okay, so this is the ORAM stuff I'm going to skip. I love ORAM. It's just a beautiful, elegant algorithm. I'll use another opportunity to convince you that it's great. Fast forwarding onto the last slide, right? And so lots of innovations have already happened. Not so much on latency, but significant improvements in bandwidth and capacity. The problems that remained, there's deep hierarchies, latencies to navigate those deep hierarchies, lots of data movement cost, which is why PIM has some potential, right? We have seen some early industry prototypes, and we expect people will invest a little bit more on this. And I think it's a very fertile ground for people to play in, ranging from architecture all the way to algorithms. All right, with that, I'll conclude. Take a couple more questions.
Few minutes for questions.
Yeah, go for it.
So for non-volatile memory, can
Yeah.
you say which algorithms have successfully used it, given the limit on how much they can be written?
Yeah, so I don't have, so clearly database workloads which have, write once, read very often, right? All of that helps, right? And so when you have workloads that are more dynamic, actually I should repeat the question. So the question is, what workloads are a good fit for NVMs? And so, if you have workloads that have more dynamic activity, I think there have been successful efforts in kind of getting them to work. They need additional software layers, right? So usually you won't just have the non-volatile memory, you'll also have a DRAM substrate that comes before it, right? And so one of the bullets I kind of fast forward through, the Octane memory, when it's attached along with DRAM, the DRAM is used as a cache. And so you'll have to find ways to kind of put the most volatile, or not volatile is the wrong word, right? But the most frequently changing data sets in DRAM, and then find a way to kind of periodically flush that onto the NVM, right? And so if you modify the software enough to localize the hot data, then it can work. Yeah, but it is a challenge, and I think it's a good problem to work on.
I'll just mention a few years ago, we wrote a paper on write-avoiding algorithms, which identified some where you could minimize writes compared to reads, and others where you couldn't.
Great.
Yeah, just wondering if any progress has been made.
So it's a little bit outside my core expertise, which is why I have not kept up with all of this. But this is the first time I've heard of it, and it sounds great, right? I've heard of cache oblivious algorithms and things like that. This is a neat thing to look at, and probably a good topic of further discussion in the workshop. Yeah, but NVMs, endurance is a huge issue, right? The number of writes that you can do is of the order of 10 to the power 8, right? Which is not a lot. And so you want the device to last 3 years and not have more than 10 to the power 8 writes, right? So that's a big problem. Any other questions? I guess time for one more, maybe? Yeah, go for it.
Well, I probably have a question because in the boot camp, there are many people doing computes, and they have comments on Moore's law saying that Moore's law is not working more on compute because like for energy, for cost, etc. So I'm wondering, there's a similar problem for memory. Like, can we proceed memory to make it denser and cheaper and more energy saving? Is that a continuous trend, or it's facing
So the question is about whether scaling is projected to decline for compute. Can we expect the same thing from memory as well? And the answer is yes, right? And so just like we've been able to squeeze out a few more technology nodes on the compute side, the same thing has been happening with memory as well, right? We are continuing to squeeze out a few more technology nodes. DRAM is implemented a few generations older than compute because it's supposed to be cheap, and it's not as high quality as the latest compute that you can get. So maybe we can eke out a couple more generations on the DRAM side, right? Because we have to kind of catch up with what's happening on the compute side. But all of these scaling challenges persist here as well, right? And we're just kind of trying to ride it for as long as we can. The push to non-volatile memory is partly because of that, right? We are kind of hitting the limits of technology scaling, and that's what is motivating us to find other materials that can serve as memory.
All right, thank you, speaker.
Thanks.